Fantastic. So thank you so much for the invitation and for granting us this generous award. It was obviously very nice news to open an email that says congratulations. And I'm on the job market. Very often you get an email that doesn't say congratulations. So the paper that Alessandra and I wrote is actually born out of when she was visiting us in Barcelona at the Autónoma, which is where I am, but she's also affiliated in Turin and now in Bologna and many other places. So what we want to do in this paper, which is I think quite different from what we've seen thus far, is to take this to take a discussion about climate and temperature change and economic reactions to a macro level, which is partially owed to the fact that both of us are by trade more macroeconometricians, so we spend probably too much time thinking about monetary policy shocks rather than thinking about climate shocks, which is what we want to do in this work. And beyond just this conference that we are at here, there's obviously growing evidence that people are paying increased attention to trying to understand, not only at the micro but also on the macro level, the sources and consequences of climate change. And that is obviously motivated by a want to inform policy decisions, for example, to compute things like the social cost of carbon. And what's very curious to us about this is that this is very typically done by focusing on two sides of a story separately. What does it mean? It means that I either look at how an emissions impulse affects radiative forcing and thus temperatures, conditioning on the economy, or I want to figure out how temperature change, cyclones, disasters, etc., affect economic outcomes, conditioning on climate variables. But since we believe that these things are interacting and that there is endogenous feedback between the economic system and in our case will be temperatures, but the climate system at large, what we want to do in this paper is to model things together. So I put you two examples, which I think are very nice papers of the Montamans. So James Stock, who was the advisor also in the Obama administration for environmental policy, has a lot of work on these subjects, looking at how carbon impulses changed radiative forcing. And then there's this review of Newell that goes in the direction that we saw in the presentation in the beginning, which is basically a test of what happens to GDP as temperatures change. And you can see even beyond the sort of smallish framework that we have between 20% changes, that this can be between -300 and +300 changes in GDP, depending on what you use. So not much of a consensus established as of now. So what we want to do is join these two kind of strands and say, okay, so why do temperatures, in the case of the US, by the way, we focus only on the US here, vary? And at the same time, try to understand what the consequences of these temperature changes are. And a way to incorporate these things in an empirical framework is to use time series techniques, which is something that is traditionally a little bit late to the game. So a lot of the innovation tends to happen on the micro side of things. And the time series guys like me, they come a little bit later. So there's lots of work now being developed. Felix Pretz, I think, was mentioned earlier also. Nathan co-authors came out last year, and this Monday, I think, Bilal and Kenzig published a shocker of a paper, which is in the NBER working paper series, which basically says that our estimates are off by a factor of 10. So we want to step into this kind of literature and contribute there. And add to our already somewhat complicated life the complication that the United States is a very diverse, heterogeneous country in terms of industrial organization, in terms of climate dynamics, etc. So what we want to do is we want to find a way to allow for spatial heterogeneities in the macro model. So the contributions that this paper brings is to say, well, the methodology that we propose has not been used thus far to study the feedback between temperatures and economic variables, which is done using a model that incorporates spatial heterogeneity to the use of principal components or factors. In the time series context, this has been used very extensively to study business cycle movements, but we can transport this idea as well to the causality analysis of temperatures and economic shocks. And what we want to do here is to use identification techniques that are internal to the model, in the sense that I will not necessarily just assume that temperature is an exogenous object, because there's quite a bit of evidence surging right now, especially the sort of in the wake of the COVID pandemic, that the effects of human activity on temperature changes are much more fast-lived than we thought previously. So we'll embed things into this methodology. And to give you a sort of snapshot of what I think are some of the important results of this paper is going to be that first up, reduced form evidence, which will be purely descriptive, is to say that, is it valid to say there's a climate shock, a single one? It turns out that that's probably a partial story of something, because it turns out that you need a substantially higher number of exogenous movements in temperatures to describe what happens in aggregate movements in temperatures in the US. Here we propose to say between 4 and 5. I'll go into more detail there. And then there's a reduced form connection between the economic activity in the US and temperature movements, which seems to run through TFP, which is good because that confirms some of the micro evidence that says, for example, if it becomes very hot beyond 26 degrees, you're very much less productive. But we will show that actually the way that this looks suggests that it's actually the causality seems to be running the other direction, that you have an increase in TFP, which leads to emissions exchanges, which then influences temperature movements, which doesn't preclude the other mechanism, by the way. It's just something on the macro level that seems to be more important. Okay, and then in terms of the causality results, we're going to be identifying 3 sort of standard macro shocks as proxies for what drives the majority of economic activity in the US, and study basically the impulse responses of temperatures everywhere. And what turns out to happen is that actually you see localized cooling as a response of these two technology shocks in areas where there's a lot of manufacturing and energy producing industry in the US, which tends to be located towards the southeast of the country. And then we have investment and labor supply type shocks, which actually lead to the warming that we all expected to see, which can be explained by a trade-off between different emissions of different gases, that aerosols and greenhouse gas, but I'll talk about that in more detail. Okay, so there's somewhat surprising temperature movements induced by human activity there. And then we have conditional on all these observations. What we see is that the type of temperature shocks that people have investigated, I said earlier, probably you need more than one, so I'm going to propose 9, all have something in common in the sense that they produce the shape that we observe in the literature, which is you have sort of small reduction of output in the case of the US, but they tend to be very ill measured, so it's very hard to find significant reductions. And it turns out it actually matters how you interpret what an average temperature change is. Does that happen in a specific location? Does that happen everywhere? If it happens predominantly in the West, it actually turns out that this can even be expansionary. Okay, so after all that, let me talk about the data, these model setup, and then talk about these descriptives, which are important for this paper. So the first part is the temperature data, which you can get several spatially interpolated data sets, which basically map temperatures everywhere across the globe at a somewhat higher or lower resolution. In this case, we use the one from the University of Delaware, which is a 55 by 55 kilometer grid. That gives you on the global scale around 65,000 time series starting in 1990. Since we focus on the US, that's still a relatively large number of around 3,500 time series that we have to incorporate into this model for just the contiguous United States. And what we're going to be doing is, well, in time series, so if you have something like 3,000 time series, it's very hard to model. So you need some kind of dimensionality reduction technique, which kind of helps us in this context a little bit as well, because you get rid of some of the measurement error concerns that you have in these interpolated time temperature data sets. And we will pair that reduced set of temperatures with standard macro aggregates that people study. This is going to be just GDP investment hours and TFP, the utilization adjusted series of Fernald used. Why those series? Basically, those are going to be needed for our identification proposal, and people generally focus on GDP. That's probably a good debate to have if that's the best thing to do. But you can replace certain variables. You can look at consumption. You can look at other outcomes. The results are pretty much in line. And we're going to be doing this at a somewhat high frequency, which will be quarterly. Focusing on the post-war sample, essentially. So on the lower end, this is basically capped by the TFP availability. On the higher end, this is basically capped by the temperature data. You can change this to the CRU dataset, for example, that is available on December 2022. Nothing changes. If anything, we get even better results, which I probably should change. But okay. First observation. This, I think, is already very interesting. So if you have such a rich data set, somehow the reflex in the literature seems to be, well, let's reduce the dimension by taking an average of these temperatures. Typically, this is done by some weighting measure. So I take the population at the grid cell level, and I try to obtain a measure of temperatures that is weighted by population density over population at large at the grid scale level, so that I measure temperature changes in areas where people actually live. And it turns out that whether you do that or not, where you use the raw data, if you do that and you regress, here it says PC, but it's the first principal component, it's the same as the average. If you regress that on every grid cell in the United States, what you get is this picture, this red, egg yolk in the middle in the Midwest, which tells you, okay, so this is actually where you pick up a signal of temperature change. You basically miss the entire West Coast, you miss Florida, you miss some parts of New England, where there's a lot of economic activity happening. So that's going to be somewhat tricky. If you take the kind of population weight, it's going to shift a little bit to the right. It's going to move a little bit towards the East Coast. Why is this happening, by the way? There's a lot of hot air coming from the south and a lot of cold air coming from the north in that area, which is why that's the tornado kind of or hurricane kind of corridor, which produces a lot of temperature variability. Measures like principal components that are going to try to find variability are going to react mostly there, but they carry the same signal as the average. So solution, use more information. Instead of 1, use 8 principal components. You get a much better coverage of explained variances. If I want to understand what's driving global warming or things like that, and I should hit everything. Okay, so but you can increase that number ad absurdum if you want, but eventually you will run into parsimony problems, right? So here we use 8. The model setup, so tiny bit of time series econometrics, is basically inspired by the model of Bernanke co-authors who want to study monetary policy using hundreds of macro series. Here's hundreds of temperatures, thousands of temperature series. The idea is to say I have a measure of temperature at location I at time t, and I'm going to assume that I can decompose this into essentially a common component, which is this lambda times yt, and an orthogonal idiosyncratic component eta t. I will focus exclusively on the common component because in our definition or understanding of global warming, things that drive temperatures at scale everywhere should be captured by a common component. What eta t will represent is measurement errors, localized effects, sectoral effects, regional effects, which I'm not saying are not relevant for macro movements. They potentially are. I just can't focus on them in this setup. And I want to focus on everything that happens in yt. So yt will just be made up of the principal components that I showed you earlier and some of the economic data. Dynamics are governed by a standard vector regression. And what we want to do is we want to now identify structural shocks, which can be done by pinning down an orthonormal matrix H here using standard techniques that are discussed in Ramey's handbook entry. The objects of interest for that then are the impulse response functions, which are going to be this lag polynomial k and the lag polynomial lambda ika, which is nice because it allows me to gets me the 4 impulse responses for the economic variables and 3,500 impulse responses for temperatures everywhere. Okay. Now, obviously, identification here is key. So how do we pin down these objects H? Well, we're going to rely on frequency domain techniques that have been developed or revived, let's say, recently in the literature for business cycle analysis. For example, Mario Forni and co-authors have a paper on this. The idea is basically to say I decompose every single time series into frequency components that can be high fluctuations, so a kind of erroneous component, that can be business cycle fluctuations, that's basically something between 6 and 32 quarters, and then you can have low frequency movements, which captures by and large the trend in the data, which is where we expect to see most of the action happening, since we all sort of agree that 99% of researchers agree that most of the uptick in temperatures is it can be attributed to anthropological activity. Why is this nice? Well, because it allows us to, it actually coincides quite nicely with frequencies that you actually observe also in temperatures. For example, we just finished an El Nino episode. These ENSO variations that affect temperatures globally last between 2 and 7 years in an unpredictable fashion. You have solar cycles that can be up to 10 years, for example. And we can pretty much, these coincide with the definitions of economic cycles. So now cardinal sin, yeah, huge table in the presentation, not a good idea. So and it's a super complicated table also. So I'll try to walk us through this. Basically, what's happening here is this is a reduced form exercise. I'm saying, okay, I know how to figure out the main things that drive cyclical movements in all of my temperature data. I don't care what they are at this point. I just want to how many of these things do I actually need in order to explain a sufficiently high share of variation in temperatures everywhere? So then I have to average, because otherwise I have to show you the table that's even worse with 3,500 temperatures. And what you see is a 1, 2, 3, 4, 5. It turns out I need 5 to surpass the threshold of 80% in every of these bands. So low frequency is 83 after 5. Business cycles, the same 5 shocks give me 87. High frequency, the same 5 shocks give me 86, 4 or 5. And what's really interesting here is if you jump from the 3rd to the 4th shock. So if I, instead of 3, I include 4 maximizers here, I have a big jump in low frequency temperature movements that are explained, a big jump in TFP at low frequency explained, a big jump at TFP explained at business cycles, and in GDP as well, by the way, and in hours worked. So a clear connection between, without targeting any of the economic variables, between the frequencies, business cycles, low frequency, high frequency variation in economic variables, and the low frequency component of temperatures. So there's a connection. However, this connection looks more like that something is changing at the side of the economy at a high frequency and has an effect on temperatures only at the low frequency, so sort of in the long run. That looks more like an economic shock to me. So, but I can't answer that without doing a causal identification, right? So here, this is preliminary evidence to say there is a connection, and I have reason to study this. Okay, so let's jump ahead and say, well, let's figure out 3 main shocks. Think about the aggregate production function, basically. So you have a technology shock, labor supply shock, and investment shock. That's in the macro literature. Justiniano and co-authors have a bunch of papers where these are the 3 that are proposed as driving output up to basically 90% output. So we use these because output, in theory, is related to emissions. Emissions will then affect radiator forcing, and radiator forcing will spill back onto temperatures. So let's identify these objects. Technology shock is standard kind of long-run identification from Galli. Investment shock is the main shock driving business cycle investment, which is the Auclair kind of Hank model derived identification. And the labor supply shock comes a little bit further back, from the 1980s. Some papers that show you how to identify this as the main component of hours worked in the long run. These, by the way, they're sort of boring because they're already, people have done these, right? So it's just to show you that they're not crazy. So you have a supply type shock, a technology, supply type shock for labor, and it's kind of AD looking shock for investment, which has a very specific hump-shaped response. So it's very easy to think about, it may be easier to think about this in terms of ASAD. So you focus later on technology and investment shock, which is where the results are the clearest. And here, this is the Adobe Acrobat magic. So this took me a long time to make, so I was worried that this wouldn't work. So basically what's happening now is you have a map with these 3.5 IRFs. I can't show you the magnitudes, unfortunately, because that would be a 4th dimension. I needed a 3rd dimension for that. And you will see blue dots, gray dots, and positive dots. And red dots. So responses that are negative will be blue. Everything that's insignificant will be gray. And what's an increase in temperatures will be red. And if you run this, what's interesting, this is a technology shock. If you run this, so you have a little bit of dancing, and then you get a lot of movement, a lot of blue dots happening. And as you extend the forecast horizon of the impulse responses for 10, 15 years, that actually recedes essentially. So what's happening here? I have a permanent, so you turn on the car and you leave it running. So you have a continuous flow of emissions happening, and especially towards the side of the East Coast and the West Coast. By the way, if you have 3,500 IRFs, you will not get all of them to do what you want, right? So there are going to be dots that are weird. But okay, so you get a sort of more or less clear picture that in this side of the country, there's a lot of cooling happening, which is weird. This is, Konstantin and Alessandra Trump is not be here. And no. So what's happening is this can to some extent be explained, which I will show you later, that there is a consistent increase in aerosol emissions, which is much larger than the simultaneous increase in greenhouse gas emissions. And aerosol emissions can actually lead to localized cooling. And the reason that this then recedes towards the end is that the greenhouse gas effects take over. So maximum greenhouse gas effects tend to happen around 15 years. Can last up to 200 years. I can't project up to 200 years with a Favre. That doesn't work. If I do this, on the other hand, for investment, you have a little bit of something else, the impulse response dancing that happens in the first couple of quarters on the impact that can have. So what happens now is that you have positive responses spreading essentially over the entire country. So here they don't seem to be receding as you go up to the horizon about 60 quarters, right? So here, and this is curious because actually what you have here is a very strong greenhouse gas impulse, which takes a little bit longer to recede, but you have essentially no or a very small impulse in aerosol emissions, which is not strong enough and not sustained at all. So that cooling effect tends to be gone essentially immediately. That's why this effect is much faster in materializing warming. I don't have methane, so I actually presented this a while back in Oxford. And I said I want to incorporate methane, and I was told that the data from that you can get from the EPA is SHIT. So I should not have used this. So we're kind of refraining from that for now, but these effects are reasonable. Here's the picture for that. So what's happening is the SO2 is one of the most prominent aerosols. After the technology shock is a very large impulse that is up to 4%. You can see the car stays on, right? So you keep emitting these things. That's why this doesn't go away. It looks like for 15 years after the impulse, they're still cooling. No, it's because this is still turned on. It's not a one-off impulse. And for CO2, that's much larger. And then you have basically a reduction after the demand type shock in SO2 and a much more persistent and strong impulse in greenhouse gases for SO2 here. Now, once I've identified these effects, I can go ahead and say, well, conditional on this, I still want to know what temperature change does with the economy. And I said earlier that this is something. The reason that there are so many papers is that it's very hard to say what the specific shock should be. So most of people try to construct sort of an instrument or try to get an exogenous measure into the model. And here I can do it from within the model. I can say, find me the shock that explains the most low frequency temperature movements in the entire country. Find me the shock that explains the full spectrum of movements everywhere. Find me the shock that explains movement in the coast and not the coast, in the West Coast, East Coast, and the Gulf. And so you can keep doing this until you get even more gray hair than I got in the last year, or the short run. And actually, all of them produce pretty much the same picture. So you have a small, most of the time, insignificant reduction. There's a lot of uncertainty given the modeling choice that we made here. But this is the typical picture that people get. So the US seems to be sitting, unless you're the Bilal-Kensicht, then you have a social cost of carbon of $1,000. But the US seems to be sitting at a sort of bliss point that is sufficiently large, sufficiently advanced, sufficiently diversified that if there's a movement in temperatures, it doesn't seem to topple them and then start all the nice political economy discussions and you want to have maybe. Except for the West Coast, by the way, this is interesting. So if you target the West Coast, by the way, all of these are scaled. So there's a 1 degree Celsius average increase in temperatures in the US, which is what people usually do. But if you think about it, what does it mean, 1 degree medium? I can get a 1 degree increase by changing one of these 3,000 stations and leaving all the other ones at 0. I want to have an aggregate movement. So the West Coast, what does it do here? I take the data that tells me, okay, when I do that on the West Coast, simultaneously temperatures seem to be lower actually at the same time in the East Coast. At the West Coast, it can be beneficial. At the East Coast, the lower temperatures are beneficial, and that's positive. Okay, great. So I will conclude here. I have no idea how I did on time. Okay, so it turns out that heterogeneities, even for the country of the US, seem to matter in terms of how GHP responds to changes in temperatures that are, on average, producing the same thing but hitting different parts of the country. But by and large, we confirm the results that people have found, which is small negative responses. And then we see a very strong influence of US economic activity. By the way, I didn't quantify that earlier. So that's about 25% of the low frequency component in that country, which is very similar across the globe, is attributable to these 3 US economic shocks. That's roughly the cumulative share I think they have in CO2 emissions. So that's sizable. And then we have these cooling effects from aerosols, which I think from a policy point of view is also important. So you know that probably in Europe and the US, we're quite successful in getting rid of these emissions. It's essentially down to 0 in the last years in the US. There's, of course, countries where that's not the case, where such as India or China, for example, where this comes from burning coal. This is still a very significant factor. So once that's removed, prepare for more warming at faster scale. And then the warming from the greenhouse gases, it seems to be spreading out gradually over the country. Okay, so I finish here. I have a nice picture in the end, which is, by the way, so when you think that like this principal component thing of averaging temperatures applies only to the US, this happens also in other countries, right? So in China, there's the Himalayas, okay, so not such a big problem where this blue thing here in the lower corner, but in South China, you miss quite a bit, South India, you miss a bit, in Australia, you hit the outback. In Europe, Spain, Portugal, Greece, basically, okay, Iceland, not much surprised that you missed that. And in Brazil, to some extent, and okay, Canada, you hit basically also deserted places. Okay, so I think that's also it. Sorry. Thank you very much. Please.
It's interesting also the part of the effect of temperatures on, you know, is an whole effect of temperatures on regional and very interesting is the cooling effect. Also, the feeling is that gas emissions and we think of greenhouse gas emissions something which contributes global concentration of CO2 and that
Yes.
over long periods of time global temperature. And that, of course, distributes differently over the world, but with no connection in source.
Yeah, so
something that I've been missing in how you establish results.
So I think one of the missing pieces here could in fact be methane emissions or gases that have faster potentially effects that we sort of don't have here. What you can also see to some extent, so I think, yeah, the localized effect of CO2 itself is understudied. I think that doesn't, yeah, probably needs a bit more research. What also happens is that you actually get a reduction in aerosols. It's small and it's insignificant, but you can think of things. So it's an investment type shock, for example, that leads to, by and large, unproductive capital ramping up and hiring people, which is not necessarily TFP related. And for example, in the 1970s, there were these legislation changes and the technology changes, which installed things like scrubbers into power plants, which is in essence an unproductive capital investment that would probably be triggered by this shock, which leads to a reduction in aerosols. If that's gone, that can also lead to localized warming. So there are several channels that can contribute. I think obviously the most convincing one would be to, my idea of, I guess fantasy, would be to have the same map that I have for temperatures, for emissions. And then, I mean, in some sense, there's evidence for that these effects seem to be happening because we're measuring them. What gas specifically is ultimately responsible for them, I would have to show the direct evidence of all the responses at localized level, but I don't have that data. Yeah, so the JRC, I think, has, sorry? Odiac, I don't know. Can you, if you can hook me up with data. So yeah, the JRC has data annual frequency as of the 70s at a relatively high resolution, which is something that, we're trying to make fit with this identification, but we haven't done it.
There's also CO2 stays in the atmosphere for, emissions. Survey translation of local temperature from local emissions over short periods of time. However, I mean, CO2 greenhouse gas emissions, CO2 emissions, are also as or associated, closely associated to emissions of other gases which have low, impact, which also may translate. Are measured with.
So we're getting a net effect without being able to say X, Y, and Z are the contributors to that. That decomposition, I think, requires more data. But apparently it exists, which is awesome. I have another paper. Other questions? Slide is not missed. That's good. So thank you very much.